So let me start the presentation. Can you see the presentation? So the chapter's name is Essentials of Pharmaceutical Chemistry. So what is the chemistry of pharmaceuticals? We will study in this. First, we'll start with introduction. Inorganic pharmaceutical chemistry is a science that makes use of the laws of chemistry to study inorganic substances as drugs, that is their preparation, chemical nature, composition, structure, etc. This unit presents the basic concepts of pharmaceutical inorganic chemistry with emphasis on description, mechanisms, and uses of various pharmaceutical products which are clinically used to correct various bodily disorders. So, in this chapter, we'll study the inorganic pharmaceutical chemistry, and in the next chapter, we will study the organic chemistry. So, what are the objectives of this unit? Understand the various concepts of acids and bases and their importance in pharmaceutical chemistry. Explain the role of buffers in pharmaceutical preparations, their mechanism of action, and the buffer systems present in the body. Discuss importance of various intra and extracellular electrolytes present in the body fluids and list various inorganic preparations used to correct the diseased conditions of the gastrointestinal tract along with their mechanisms of action. First, we'll start with acids and bases. So you may have studied about acids and bases in your previous classes. We are summarizing the theory of acid and bases here to enable you to recall it. So first, what is Arrhenius acids and bases? Arrhenius defined an acid as any compound that releases protons, that is H plus. H plus is hydrogen atom without any electron, that is protons, H plus, in water, and a base as any compound that gives OH minus ions in the water. So the Arrhenius acid will react with water to form H plus and A minus, and Arrhenius bases will react to form B plus plus OH minus. Then there are different types of acids. First one was Arrhenius acids and bases. Second is Bronsted-Lowry acids and bases. According to second definition proposed by Bronsted and Lowry, an acid is a proton donor and base is a proton acceptor. So an acid is a proton donor, proton to any compound, proton from any compound, so that will be called as. So in this reaction you can see Ha plus B, Ha is the acid and B is the base, then H is transferred to B and A becomes A minus, that is called as conjugate base, and BH plus, that is called as conjugate acid. Then third type of acid base is called as Lewis acid base. Despite the usefulness of Bronsted-Lowry definition, there is an even more general definition of acids and bases provided by G. and Lewis. The Lewis model of acids and bases proposes that an acid is an electron pair acceptor and while base is an electron pair donor. This is opposite to the previous theory. In Lewis model of acid and bases, it proposes that acid is an electron pair acceptor while a base is an electron pair donor. Now we come to the concept of pH. To speak of acid or base strength, we need scales for acidity and basicity. The pH and pOH scales are quantitative representations of these values for acid and basic solutions. A very convenient concept called pH was proposed by Sorensen. He defined pH as negative log of hydrogen ion concentration. It can be expressed as this relationship. pH is equal to log 10 of 1 upon H plus, that is minus log 10 of H plus. The prefix P is front, in the front is the symbol, means that we are taking the negative log. For example, in a solution where a hydrogen ion concentration is 10 to the power minus 3, we therefore have pH is equal to minus log 10 to the power minus 3, that is equal to minus 3 is equal to minus minus is plus, so pH is equal to 3. Similarly, POH is minus log of OH. So log Kw for the from the equilibrium expression for the dissociation of water, log Kw is equal to log H plus log OH minus. Or we can say from this definition that pKw, that is the dissociation constant for water, is pH plus pOH. So pH plus pOH should be around 14. It should be 14. So neutral pH or pOH is 7, and anything that is below 7, that is acidic, and anything which has pH more than 7 is basic. Anything which has pH less than 7 is acidic in nature, and anything that has pH more than 7 is basic in nature. So we can see from this table, anything that has pH less than 7 is acidic solution. Any pH that has 7, that is neutral solution, and any basic solution is pH having more than 7. Now, what are buffers? A buffer solution is an aqueous solution consisting of a mixture of weak acid and its conjugate base, or a weak base and its conjugate acid, whose pH does not change on addition of small amount of acid or a base. So the pH doesn't change if we amount a small amount of acid or base in this buffer solution. That's why it is called as buffer, because it doesn't changes any pH, because it is a combination of either a weak acid and its conjugate base, or a weak base and its conjugate acid. So buffer do not change their pH values. Also standing for a long time will not change any pH. Exposure to atmosphere or any slight dilution, so pH will not change in these conditions also. Thus, a buffer system are pairs of related chemical compounds capable of resisting large changes in pH of a solution caused by addition of small amounts of acids and bases. So, in buffer solution, if we add any type of acidic or basic solution in small amount, the pH will not change. Any large changes in the pH will not occur. That solution will be called as buffer solution. The buffer should not react with other chemicals in a pharmaceutical preparation. Also, it should not participate in redox reactions. Redox means reduction and oxidation reactions. Reduction and oxidation reactions together are called as redox reactions. So, also it should not participate in redox reactions, any chemical reactions which involves oxidation and reduction, alter the solubility of other components, form complexes with active ingredients, or participate in an acid base reactions other than those required function. Now we can see that the pH of blood in human body is 7.3 to 7.4, which is controlled by buffering mechanism. So our blood has also a buffer system which prevents the pH change in our blood. That's why it is called as buffer. So roles of buffer in pharmacy. The following factors are influenced by the change in pH of any pharmaceutical compound or preparation. First one is solubility. The pH plays an important role in the solubility behavior of compounds. The required pH gets adjusted by buffers. Many inorganic salts such as ferric, phosphates, borates become soluble in acid media but precipitate in alkaline media. So many organic compounds with acidic functional groups are soluble in alkaline media. Similarly, amines and alkaloids are soluble in acidic media but are almost insoluble in alkaline media. So the pH is the main factor which is determining the solubility of many compounds. Then next one is color. The color of many synthetic and natural dyes is pH dependent. Red color of cherry and raspberry is maintained in acidic pH and becomes pale yellow to nearly colorless in alkaline pH. So the second point is color, which is maintained by the buffer system and pH dependent solution. Third one is stability of some compounds to redox conditions. The adrenaline hormone with dissolved oxygen in the presence of alkaline medium, so its solution for injection is to be buffered to most stable pH range 2.5 to 5. Ascorbic acid and penicillin are unstable in alkaline pH. So we can see that some uh, some of the compounds or hormones in our body are dependent on pH, and it will change the stability if we change the pH from acidic to alkaline or alkaline to acidic. Then the fourth point is patient comfort. If the pH of injectable and preparations for internal or external use differs greatly from the normal pH, they become irritating for the patient. An extremely acidic or alkaline pH must be avoided to prevent tissue damage. Now we come to intra and extracellular electrolytes. These are various inorganic compounds present in the body fluids, and the concentration of these in various compartments is balanced in such a way that the body cells and the tissues always have the same environment. Some regulatory mechanisms control the ionic balance, osmotic balance, and pH, which in turn maintain the concentration of solutes in various body fluids. Generally, in the body, electrolyte concentration is maintained, but if the body cannot maintain or correct the electrolyte balance, then it is done by external administration, which is known as replacement therapy. Replacement therapy. Various products like electrolytes, acids and bases, carbohydrates, proteins, amino acids, and blood products are used to replacement as per need of the patient when the balance of fluids is disturbed. In this unit, we are going to consider the electrolytes used in replacement therapy and for correction of acid-base balance in various body fluids. There are two compartments of body fluids, extracellular and intracellular fluid. Extracellular fluid is fluid found outside of cells. Extracellular fluid makes approximately 20% of total body weight. The extracellular fluid consists of blood plasma, interstitial fluid surrounding the cells, secretory fluid, which is fluid in transit, and dense tissue fluid, which is water located within dense connective tissues such as cartilage and bone. The second one is intracellular fluid. Intracellular fluid is the fluid inside the cells. It makes up to 35 to 40% of total body weight. Major physiological ions are like chloride, phosphates, bicarbonates, sodium, potassium. Now, sodium is the main cation in the extracellular fluid compartments, and potassium is the major cation in the intracellular compartments. Calcium, which is the main cation present in the bones. It is composed of 99% in the bones. Then magnesium. The role of major physiological ions. The major role of physiological ions is to control osmosis of water between body compartments. So because there is difference in concentration of bodily substances or bodily fluids. It controls osmosis between higher concentration and lower concentration of any particular physiological ion. Then, to maintain the acid-base balance needed to perform normal cellular activities. Then, to generate action potentials and graded potentials and control secretion of some hormones and neurotransmitters in the nervous system. Now, electrolytes used for replacement therapy can be, some examples are sodium replacement by different sodium compounds, or potassium replacement by some potassium compounds, calcium replacement by Ringer's injection or calcium gluconate and other compounds. So, next point is physiological acid-base balance. In the body, acids either as carbonic acid from carbon dioxide or lactic acid from anaerobic respiration are constantly being produced during the metabolism. Carbon dioxide and lactic acid is formed by respiration. Since most of the reactions occur only within a very narrow pH, that is 7.38 to 7.42, the body utilizes several buffer systems to maintain the pH in the body. That is the proper homeostasis of the body. Two of the major buffer systems in the body are bicarbonate carbonic acid buffer found in plasma and kidneys, and monohydrogen phosphate dihydrogen phosphate found in cells and kidneys. So these are the main buffer systems present in our body. Bicarbonate carbonic acid buffer in plasma and kidneys, and monohydrogen phosphate dihydrogen phosphate buffer found in cells and kidneys itself. Now, if the body can restore the pH back to 7.35 to 7.45 by alteration in the respiration and kidney function, it is referred to as compensated metabolic acidosis or alkalosis. If it is able to maintain the pH of the blood, then it is called as compensated metabolic acidosis or alkalosis, depending upon which type of compound has been increased in or decreased in the buffer system. Now, electrolyte combination therapy. These are usually two types of solutions used in replacement therapy: a solution for rapid initial response and a solution for subsequent replacement. So, electrolyte combination therapy can also be used, and not singly, we can use it in combination. And there are two types of electrolyte combination therapy. First one is rapid initial response therapy, and second one is subsequent replacement therapy for any solution. Examples are Ringer solution, lactate Ringer solution, or oral electrolyte solutions such as ORS, that is oral rehydration salt solution. Now, gastrointestinal agents. The digestive system in the gastrointestinal tract, which is a group of organs extending from esophagus to anus, is called as gastrointestinal tract. Whenever the above functions go wrong in digestion or any type of buffer system in the gastrointestinal tract, there are possibilities to occur diseases or undesirable conditions. For example, when there is inadequate secretion of acid in the stomach, this causes achlorhydria or hypochlorhydria. Whenever excess secretion of acids take place in stomach, it causes imbalance of acid enzyme ratio, finally leading to hyperacidity and ulcers. There may be accumulation of toxic substances or gases. There may be inadequate absorption of fluids and minerals from large intestine, thereby causing diarrhea. There may be insufficient peristaltic movement of large intestine, causing constipation, or there may be possibilities to occur ingestion of poisonous substances accidentally or intentionally. Now, drugs for gastrointestinal diseases. It is possible to correct the above conditions by administration of suitable drugs, which include products for altering gastric pH. If the pH in the gastric mucosa or gastric acid changes, there are some products which can alter gastric pH and it can normalize the gastric pH. Then second one is protectives for intestinal inflammation. There are some protectives which protects from infection and inflammation of intestinal mucosa. Then there are cathartics or laxatives for constipation. Now some products for altering gastric pH are acidifying reagents or acidifiers. The most commonly used acidifying agent is dilute hydrochloric acid. So if there is any destruction of gastric hydrochloric acid functioning cells, so if there is any hypochloridia in the gastric mucosa, means there is lesser amount of hydrochloric acid in the gastric region, there is a replacement therapy in which we we can use dilute hydrochloric acid for proper maintenance of gastric acid. Then there are antacids. You must have heard the antacids. If there is excess production of hydrochloric acid or hyperchloridia, then the antacids can be used, and the antacids also provide symptomatic relief from pain by neutralizing the excess of hydrochloric acid and helps in reducing pain due to ulcer. So it can prevent ulcers also due to excess hydrochloric acid, and it can neutralize the hydrochloric acid which is excess in amount in the stomach. Types of antacids, it can be aluminum compounds, calcium compounds, magnesium compounds, or sodium compounds. Depending upon whatever we need, we can change the composition of the antacids. Now, protectives and adsorbents. These are chemically inert substances which are used in the treatment of mild diarrhea or dysentery or other GIT disturbances. Protectives or protectants are used to form a protective layer on the painful ulcers in the GIT. So there are different substances which protect the intestinal epithelium from any type of injury or any type of inflammation. These are called as protectives and absorbents. These can be like bismuth compounds and milk of bismuth. Then there are cathartics, purgatives, and laxatives. In normal conditions, defecation occurs by peristaltic movements of the intestine, which occur about 3 to 4 times a day. That increases the peristaltic movement of the intestine or the to and fro motion of the intestine, and that's why we can we are able to defecate the feces. Ignoring the urge to defecate and other factors like weakness of intestine, intestinal spasm, injury, diet, or as effects of other drugs leads to constipation. In this condition, the fecal material becomes dry and hard. So in these cases, we can use laxatives, cathartics, and purgatives, which provide relief in constipation by retaining fluid in the bowels and are defined as cathartics. Cathartics are drugs which bring about defecation, and these are used for treating constipation and for expulsion of intestinal parasites. They may also be given for clearing bowels before surgery. What are purgatives? Purgatives are also cathartics which act similarly but have mild action. Now, milder types of purgatives are called as laxatives, which increases the amount of feces, and the peristaltic movement also increases so that the person is not constipated and the person is able to defecate. These compounds act by 4 different mechanisms, which are given below. First one is stimulants. These are drugs which act by local irritation on intestinal tract and bring stimulation of peristaltic activity. Then bulk purgatives. These are able to increase the bulk of intestinal contents, as these are cellulose or non-digestible types of materials which swell considerably when wet and stimulate peristalsis as they increase the bulk. Third one is lubricants. In constipation, contents of intestines become hard because of absorption of water. by the body, resulting in difficulty in clearing of bowels. The substances like liquid paraffin, glycerin, mineral oils, etc., act as lubricants to provide relief. Then the fourth one is saline cathartics. These act by increasing osmotic load of the intestine by absorbing large quantity of water and thereby stimulate peristalsis. Now, topical agents. What are topical agents? The term topical means pertaining to a particular spot. Topical agents are the compounds that act locally on the body surfaces like skin and mucous membrane. Now, what is the classification of topical agents? First one is protectives, adsorbents and demulcents, emollients, astringents, and caustics. Now, this chapter is over. We will continue to the next chapter, that is chapter number 8. We can take 1 minute break. Now, the next chapter is Essentials of Pharmaceutical Chemistry, second part, that is continuation of the first part. In this unit, you will learn about the fundamentals of organic pharmaceutical chemistry. In the previous unit, we learned about inorganic pharmaceutical chemistry. In this unit, we will learn about the organic compounds or organic pharmaceutical chemistry. You know that most of the drugs are organic compounds, and to understand their nature, it is essential for you to be familiar with functional groups present in organic compounds. After studying this unit, you should be able to identify the functional group present in an organic molecule, give IUPAC names of various aromatic compounds or organic compounds, list various types of isomers, and write cis trans Ze isomers of a molecule. Assign the configuration of chiral center as R or S and explain the significance of stereochemistry in a drug. Now, functional group classification. We know that there are millions of organic compounds. Therefore, it is very difficult to study each and every compound individually. Thus, by grouping similar compounds together in a class or a family, it is easier to understand their properties and reactions, etc. One way of such classification is based on the functional group. What is a functional group? A functional group can be defined as an atom or a group of atoms in a molecule which exhibits characteristic chemical properties, which have similar chemical properties, and by composition also they are having similar type of atoms or group of atoms in a molecule. You must have heard these terms in organic chemistry like alkane, which have no functional group, such as methane, alkene, which has double bond between the carbon atoms, and this is ethylene, alkyne, which has triple bond between the carbon atoms, like acetylene, cycloalkane, like cyclohexane, aromatic compounds like benzene, alcohol like methyl alcohol and ethyl alcohol, phenol which has OH group in the aromatic compound, ether which has oxygen atom in between the methyl atoms like dimethyl ether, aldehyde which has oxygen bound to carbon atom and hydrogen bound to carbon atom, that is example is acetaldehyde, ketone which has oxygen bound to carbon atom with double bond, example is acetone, carboxylic acid which has COOH composition like acetic acid COOH. Ester, which has C with double O composition like methyl acetate. Anhydride, which has COOCO, that is acetic anhydride. Then amine, which has nitrogen atom like methylamine or dimethylamine. Then imine, that has nitrogen attached to carbon atom like N-ethyl methylamine. Then nitrile, which has nitrogen bond to carbon atom with triple bond. Example is acetonitrile. Then nitro compounds which have NO2, that has example nitromethane. Then amide, which has nitrogen attached to carbon and oxygen attached to carbon, such as acetamide. Then halide, which has halogens in the compound, such as methyl chloride or methyl bromide. Then acyl halide, which has CO with halide, that is acetyl chloride. Then there is thiol, that has SH or sulfur and hydrogen molecule, that is methane thiol. Or sulfonic acid, which has SO2OH, such as methane sulfonic acid. Now, nomenclature of aromatic compounds. In this section, we shall discuss some of the rules adopted by International Union of Pure and Applied Chemistry, that is IUPAC, for naming the aromatic compounds. The aromatic compounds can have any of the following types of basic skeleton. Compounds containing one aromatic ring, such as benzene and its derivatives. Then it can be polynuclear hydrocarbons, or it can be heterocyclic compounds. First, we start with compounds containing one aromatic ring. This class includes benzene and its derivatives. The derivatives of benzene include the compounds which can have any of the functional groups discussed before attached to the benzene ring. So, if any one of the functional group which we discussed previously is attached to benzene, it is called as compounds containing one aromatic ring. You can see example is chlorobenzene or nitrobenzene. Then di-substituted benzene. This class of compounds is named either by using position numbers or prefixes ortho, meta, and para. If the functional group is present to just opposite to the group, then it is called as para. If it is attached near to the group, it is called as ortho, and if it is attached to the second number from the group, it is called as meta. So ortho, meta, and para are three types of di-substituted benzenes, such as 1,2-dimethylbenzene, 1,3-dimethylbenzene, 1,4-dimethylbenzene, that is para-xylene, or 1,2-dibromobenzene, that is ortho-dibromobenzene. Now, polynuclear hydrocarbons. In a polysubstituted benzene, the ortho, meta, and para nomenclature is no longer applicable. If the two aromatic rings are attached to each other, it is called as polynuclear hydrocarbons, such as naphthalene, anthracene, phenanthrene, or biphenyl products. Then heterocyclic hydrocarbons. Aromatic compounds containing heteroatoms such as oxygen, nitrogen, or sulfur in the aromatic ring are called heterocyclic compounds, such as this. If nitrogen is present in the benzene ring, it is called as heterocyclic compound. If oxygen is present in a 5-ring structure, it is called as heterocyclic compound. Now, international non-proprietary names. International non-proprietary names are selected by national or international nomenclature committee. The WHO or World Health Organization strives to provide one name for a drug throughout the world so that there is no confusion about what is the name of that drug. While selecting international non-proprietary names, the following points should be kept in mind. It should be distinctive in sound and spelling. It should not be too long. It should show relationship to substances with same pharmacological action. It should not conflict with any existing common names. The patient should not be confronted with names that are likely to have anatomical, physiological, or pathological connotations. Names starting with cancer would be acceptable. Example, a name starting with cancer would be acceptable for the name of the drug. Common stems have been created to show relationship to other substances of similar pharmacological actions. These are as follows. If AC is present in any type of
पता
compound
नहीं
or
यार तेरे को
it is anti-inflammatory agents of ibuprofen. Then actide, synthetic polypeptide with a corticotropin-like action. Adol or adot is a analgesic. AST is anti-asthmatic or anti-allergic substances. Astatine is antihistaminics. Azepam is diazepam derivative. Then Bactam is beta-lactamase inhibitors. These all compounds and drugs you will study in the pharmacological section of our course. Then Bol is steroids anabolic. Buzone is anti-inflammatory analgesic such as phenylbutazone derivative. Cane is antifibrillant substance with local anesthetic activity. Cane is local anesthetics. Ceph is antibiotics cephalosporinic acid derivative. Selene is antibiotics derivatives of 6-amino penicillamine. Conazole is systemic antifungals, miconazole derivatives. Cot is corticosteroids except prednisolone derivatives. Dipene is calcium channel blockers. Fibrate is clofibrate derivatives. Jest is steroids or progestogens. Gly is sulfonamide hypoglycemics. IO is iodine containing contrast media. EM is quaternary ammonium compounds. Metacin is a derivative of anti-inflammatory substances like indomethacin derivatives. Mycin is antibiotics produced by Streptomyces strains. Nidazole is anti-protozoal substances, metronidazole derivatives. Ol is beta adrenoreceptor antagonists. Oxacin is antibacterial agents such as nalidixic acid derivatives. Pride is sulfuride derivative. Pril or Prat is angiotensin converting enzyme inhibitors. Prost is prostaglandins. Relin is hypophyseal hormone releasing stimulating peptides. Terol is bronchodilators. Phenylethylamine derivatives. Tidine is H2 histaminic receptor antagonist. Trexate is folic acid antagonist, and Verine is spasmodics with papaverine like action. So every drug can be known by their functional groups, and what is the pharmacological function of that drug can be known by some of these prefixes or suffixes or the functional group in that compound or that drug. Now, what is isomerisms? Compounds that have same molecular formula but different chemical structures are called as isomers. The phenomenon is called as isomerism. Isomers can have different chemical, physical properties and biological properties. It is possible to classify isomers into various subtypes as shown. Constitutional isomers are those compounds which have the same molecular formula but have different bond connectivities. That is, the sequence in which their atoms are bonded together is different. On the other hand, stereoisomers are those isomers which have the same connectivities of atoms, but their spatial arrangement is different. We'll discuss by examples. Isomerism can be further divided into constitutional and stereoisomers. Then constitutional or structural isomerism can be further divided into chain isomerism, position isomerism, or functional group isomerism. And stereoisomerism can be further divided into conformational isomerism and configurational isomerism. And configurational isomerism can further be divided into geometrical isomerism and optical isomerism. So we'll discuss this one by one. Constitutional isomerism, if we are seeing this like chain isomers, which we discussed earlier, chain isomers are example like butane and 2-methyl propane. Both have the same molecular formula, that is C4H10, but because the structure of carbon containing atoms and their position is also different, they are called as chain isomers. There is difference in chain length. So first one is 4 carbon atoms in one chain, and the second one is 3 carbon atoms in one chain, and one is adjacent to the middle chain, middle carbon atom. Second one is position isomers. In this, the position of the functional group is different. The formula is same, C3H7Cl, but the position of chloride atom is different for the first one and second one. So it can be called as 1-chloropropane and 2-chloropropane. And functional group, if the functional group is different, then it is called as functional group isomer. So the compounds formula is same, C2H6O, but the difference in position of O is different and the functional group is also different, then it is called as functional group isomers. In the first one, it is an alcohol called as ethanol, and the second group, it is an ether and it is called as methoxymethane. It needs to be mentioned here that the constitutional isomers have different physical and chemical properties also. Then the second type of isomerism is stereoisomerism. Stereoisomerism can be configurational or conformational. Configurational isomerism, the absolute configuration of a compound can be defined as an arrangement of groups in space. This type of isomerism is exhibited by those stereoisomers which cannot be converted to each other without breaking of bonds. It can be further classified into geometrical isomerism and optical isomerism. The second one is conformational isomerism. Conformational isomerism arises due to different spatial arrangements of atoms or groups in a molecule which are obtained by rotation about single bonds. So we'll discuss one by one. First one is geometrical isomerism. Geometrical isomerism is caused by different arrangement of groups around a rigid framework. This rigid framework can be a double bond or a cyclic structure around which the various groups are attached, such as 2-butene. The double bond is present in between, but actually two different isomers corresponding to the structure can exist. In the first one, it is called as cis-2-butene, in which the methyl part in the butene is on the same side, and trans-2-butene, the second part, in which it is opposite side. So it can be called as cis-2-butene or trans-2-butene. This is type of geometrical isomerism. There are different examples of geometrical isomerism. Then optical isomerism. Optical isomerism is depicted by the optical isomers. Optical isomers are the stereoisomers which show optical activity. You must have studied optical isomerism in your BSc classes. There are many such molecules in which the carbon atom is linked to 4 different substituents. Optical isomers are molecules that are non-superimposable mirror image of each other. Such isomers are called as enantiomers. Example, this, the enantiomer of 2-butanol. It is mirror image of each other, but it cannot be superimposed on each other because the C2H5 is present on the left side in one compound and C2H5 is present on the right side in one compound. So these are called as enantiomers or optical isomers. Designation of configuration R and S nomenclature. The term configuration at a particular stereo center refers to the actual arrangement of substituents in space. Thus, the enantiomers differ from each other in their configuration around the center atom. The absolute configuration of a particular molecule can be assigned according to R and S system. If the When the molecule is viewed in a way as suggested in step 3, the remaining substituents 1, 2, 3 appears as spokes of wheel with the carbon atom at the center of the wheel as shown below. So if it is clockwise, then it is R, and if it is anti-clockwise, then it is S. Now, significance of stereoisomerism. There are many types of organic drugs and stereoisomerism is present in these type of drugs. So we can study one of the historical drugs which is called as thalidomide tragedy. Thalidomide is a non-barbiturate CNS depressant which was marketed first in West Germany in 1956. It found worldwide acceptance as an effective hypnotic, having no morning hangover by other countries like UK, Japan, Canada, and Sweden. Thalidomide was consumed by a large section of expectant or pregnant mothers to ward off morning sickness, the unpleasant effect of early pregnancy. But Dr. McBride, an Australian, reported the association between thalidomide consumption and congenital deformities in the babies which were born. Babies with malformation of limbs were born to the mothers who consumed thalidomide during pregnancy. So there were large instances of congenital deformities in the babies who were born, whose mother used to eat this thalidomide drug for morning sickness. So it was found that thalidomide is the main culprit drug which cause congenital anomalies or congenital deformities in the babies. It was reported in 1970 that R isomer of thalidomide has a favorable sedative effect, while S isomer causes prenatal deformities. So, different stereoisomers can have different effects in the body. Okay, I think this chapter is also over. You can study the summary in the free time, and we will start with chapter number 9 in a minute. Next chapter is concept of synthetic drugs. Pharmaceutical chemistry is concerned with discovery and synthesis of compounds for biological evaluation as potentially new drug therapies. It embraces the identification, design, synthesis, isolation, and chemical characterizations of such compounds. So the objectives of this unit is describe the objectives of synthetic medicinal chemistry and its development, describe the various advantages of synthetic drugs over natural drugs, describe the importance of structure activity relationships in pharmaceutical chemistry, and discuss the structure activity relationships models and QSAR. So, importance of pharmaceutical chemistry. First, the primary objective of medicinal chemistry is the design and discovery of new compounds which can be used as drugs. The discovery of a new drug requires not only its design and synthesis but also the development of testing methods and procedures which are required to establish how a substance operates within the body and acts as a drug. What are drugs? Drugs are chemical substances that are used to prevent or cure diseases in humans, animals, and plants. The activity of a drug is its pharmacological effect on the subject and it acts by interfering with the biological process. So, no drug is completely safe in allopathic medicine. New drugs, some type of side effects can happen. That's why no drug is totally free of side effects, but we have to maintain the risk benefit ratio in any drug. Means you should be able to see that the risks are lesser and benefits are more, then you can use that drug in the patients. New drugs are constantly required as the strains of microorganisms are developing resistance to existing ones. They are also required for the improvement in treatment of existing diseases and for production of safer drugs by removing the adverse effects. Type of drugs. Drugs can be obtained from natural products and drugs can be synthetic drugs. Drugs obtained from natural products. Since time immemorial, the world has been using a wide range of natural products for medicinal purposes. These products obtained from animal, vegetable, and mineral sources were sometimes very effective. These are called as natural products. Now, synthetic drugs. This wide range of pharmaceutically active compounds from the plants was used as the starting point for the development of drugs. The origin of many drugs must be looked for in substances of a biological nature, and in particular in the alkaloids. The elucidation of these structure has been starting off point for chemists to synthesize similar compounds. So synthetic drugs are produced from natural active compounds in the plants or vegetables. Today, many discoveries start with biological testing by pharmacologists of the potential sources in order to determine the nature of their pharmacological activity as well as their potencies. So there are different drugs which are synthesized from natural products also. Once a screening program has identified substances of pharmacological activity of interest, the compound responsible for its activity is isolated and used as the starting compound for the production of related drugs. The compounds on which the development is based on are known as lead compounds, while the synthetic compounds developed from the lead are called as analogs or analog drugs. Advantages of synthetic drugs. Synthetic drugs have following advantages. Useful plant compounds are often easy to synthesize. No dependency on plant collectors or growers as a source or the long-term survival of the plant. Synthetics can be patented and natural compounds cannot be patented. Now, structure activity relationship. What is structure activity relationship? The structure activity relationship is a means by which the effect of a drug or toxic chemical on an animal, plant, or environment can be related to its molecular structure. So a drug having similar molecular structure will have similar pharmacological activity also. A structure activity relationship relates the features of a drug or chemical structure to a property, effect, or biological activity associated with that substance. It constitutes a part of medicinal chemistry wherein the modification of the effect of potency or activity of bioactive chemical compounds is carried out by changing their chemical structure. Computer-based modeling methods relating chemical structure to qualitative biological activity, that is called a structure-activity relationship, and quantitative biological potency, that is called as quantitative structure-activity relationship, have been applied in many diverse problem settings. What is importance of structure activity relationship? Structure activity relationship is located at the intersection of biology, chemistry, and statistics as depicted in figure 9.1. The focused interlinking of these disciplines has brought about the development of research activity resembling the science of structure activity relationship. So in biology, the activities mechanism in the experimental process, and in statistics, the methods of analysis in the empirical process, and structure reactions in the chemistry, such as theoretical process, all interlink to form a structure activity relationship. In relating structure to activity, the main aim of structure activity relationship is to develop an understanding of a class of molecules that are active, to find out what determines relative activity, and to know what distinguishes these from inactive classes. Structure activity relationship includes the activities ranging from use of expert judgment to considerations of similarity, diversity of chemicals, to formal mathematical associations of properties and activity measures. Now, quantitative structure activity relationship. The fundamental assumption in quantitative structure activity relationships is that similar chemicals have sufficiently common mechanistic elements. Quantitative structure activity relationships is development of a relationship between structural features and property of interest so that property values can be predicted for new candidate structures. These properties include measures of potency, strength of binding of drug to an active site, inhibition of enzyme, and prediction of ADMET properties. What is ADMET? Absorption, distribution, metabolism, excretion, and toxicity of that particular drug. Now there is another term called as 3D QSAR, structure activity methods that consider the 3D structure of modeled compounds in spatial relation to one another are collectively termed 3D quantitative structure activity relationship methods. Okay, this chapter is also over. So we can continue with the last chapter for today. That is chapter number 10 in 1 minute. So the next chapter is pharmacognosy and phytopharmaceuticals. First, the introduction. The present chapter deals with the term pharmacognosy, its origin and history. It also covers the study of phytoconstituents different aspects of classification of phytoconstituents, their extraction, isolation, and characterization by different physical, chemical, and spectroscopic techniques. Pharmacognosy is concerned with the knowledge of two drugs obtained from natural origin. So the objectives of this unit is understand the importance of pharmacognosy, classify the phytoconstituents present in the plants, explain various techniques of extraction, isolation, and purification of crude drugs, and explain the various chemical and spectroscopic methods for characterization of phytoconstituents isolated from plants. Now, what is pharmacognosy? The word pharmacognosy is derived from two Greek words. Pharmakon means drug and ignosko meaning to acquire knowledge. So, to acquire knowledge of drug is called as pharmacognosy. The term pharmacognosy was introduced by C.A. Sedler, a medical student in Halle Saale, Germany in the year 1815. So the number of definitions for term pharmacognosy are used, which are as follows. Pharmacognosy is defined as scientific and systematic study of structural, physical, chemical, and biological characters of two drugs along with their history, method of cultivation, and collection and preparation for market. Pharmacognosy may be defined as an applied science that deals with biological, biochemical, economic features of natural drugs and their constituents. Pharmacognosy is the study of drugs that originate from the plants and animal kingdom. Pharmacognosy serves as a link between the following: pharmacognosy and medicinal chemistry, pharmaceuticals and basic sciences, Ayurvedic and allopathic systems of medicine. History of pharmacognosy. The history of herbal medicines is as old as human civilization. Indian history of medicinal plants is taken back from 3500 BC. A large portion of Indian population depends upon Indian system of medicine, that is Ayurveda, which have well-known treatises in Charak Samhita and Shushruta Samhita. What is the scope of pharmacognosy? Pharmacognosy as an applied science which played a crucial role in the development of different disciplines of science. The knowledge of plant taxonomy, breeding, pathology, and plant genetics is helpful in the development of different disciplines of science. The technology involving extraction, purification, and characterization of pharmaceuticals from natural resources has signified contribution to the advancement of natural and physical sciences. Classification of phytoconstituents. The medicinal potential of a crude drug is determined by nature of constituents present in it. The plant drugs chemically consist of mixture of organic and inorganic constituents known as phytoconstituents. So any plant drug chemically consists of organic and inorganic substances or compounds known as phytoconstituents. The main phytoconstituents can be classified into these groups such as carbohydrates, glycosides, tannins, and phenolic compounds, proteins and amino acids, coloring matter, lipids, volatile oils, alkaloids, resins, and carotenoids. First one is carbohydrates. Carbohydrates are defined as plant products which consist of carbon, hydrogen, and oxygen, and the ratio of hydrogen to oxygen is 2 to 1. Carbohydrates are wide occurrence in nature and provide means of storage and transport of energy and also the building blocks of the cell wall. Now glycosides. Glycosides are the substances which on hydrolysis yield one or more types of sugar or glycon along with non-sugar aglycone compounds. Now, tannins and phenolic compounds. Tannins are complex phenolic compounds which are soluble in water and have an astringent and bitter taste. Proteins and amino acids. These constitute a major class of natural product of different categories, including albumin, globulin, and conjugated proteins. Coloring matter. They are widely distributed in natural products. The majority consists of chlorophyll, and anthocyanins, and anthocyanins, etc. Lipids such as fixed oils, fats, and waxes. The term lipid is used for fixed oils, fats, and waxes. Fixed oils are liquid at normal temperature, while fats are solids or semi-solids at this temperature. Chemically, they are esters of glycerol with long-chain fatty acids. These esters are termed as glycerides. Volatile oils. Volatile oils are odorous or smelling constituents found in various parts of plants. They evaporate on exposure to air at ordinary temperature. As volatile oils are responsible for the essence or odor of the plants, they are also known as essential oils, which can be present in inflorescence such as coriander leaves, flowers such as lavender, fruits such as fennel, leaves such as eucalyptus, and bark such as cinnamon, and peels such as oranges. Then alkaloids. They constitute a major class of chemical groups present in the plant drugs. Originally, alkaloids meant alkali-like, which are applied indiscriminately to all organic bases. With course of time, the term alkaloid has altered in significance, and presently it includes mainly the cyclic nitrogenous bases which occur in plant. Thus, the alkaloids are the naturally occurring organic substances having a cyclic nitrogenous nucleus exhibiting basic properties and pronounced physiological action. Resins and resin combination. Resins are solid or semi-solid amorphous products of complex chemical nature. These are usually obtained as exudates from plants and are considered as end products of metabolism. Carotenoids. Carotenoids are responsible for many of red, orange, and yellow pigments observed in plant and animal kingdoms. Now, extraction, isolation, and characterization of phytopharmaceuticals. The crude drug contains the active constituents which can be isolated from these drugs by various methods of extraction and separation of these active constituents in the drugs. Phytochemical investigation. Phytochemical investigation or screening is the extraction, isolation, purification, and characterization or identification of therapeutically or pharmacologically active plant constituents by using different physical, chemical, chromatographic, and spectroscopic techniques. The first and foremost step in this is selection, identification, collection, and extraction of the plant material. First, the extraction. Extraction is the commonly employed technique for separation of active substances from crude drugs. It involves the use of different solvents so that it is extracted in solution form. Extraction methods. Various methods used for extraction of drugs include infusion, decoction, digestion, maceration, and percolation. Then the second technique is isolation and purification. Isolation and purification of constituents present in extract depends upon the physical and chemical characteristics of the compound to be separated. The physical techniques employed for these purpose are fractional crystallization, fractional distillation, fractional liberation, paper chromatography, thin layer chromatography, column chromatography, high performance thin layer chromatography, and high performance liquid chromatography. Now, the methods of identification of constituents. The class of compounds can be determined by their response to color tests with chemical reagents. The various chemical tests are used for detection of the following classes of compounds, such as alkaloids, carbohydrates and glycosides, phytosterols, fixed oils and fats, saponins, phenolic compounds and tannins, and gums and mucilage. So detection of alkaloid, detection of carbohydrate and glycolides, detection of phytosterols, detection of fixed oils and fats, detection of saponins, detection of phenolic compounds and tannins, detection of gums and mucilage can be done by different chemical reactions. Now, what is spectrophotometry? Spectrophotometry can be of four types: ultraviolet and visible spectroscopy, infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance spectroscopy. Okay, this chapter is also over. So today's portion is over. If you want to ask anything, then please ask students, and we will continue these chapters in day after tomorrow. Tomorrow is a holiday. We will discuss the rest of the chapters. Three chapters are remaining. We will discuss it in next class, that is day after tomorrow. If you want to ask anything, please ask. Please read these chapters so that you are able to retain the material whatever you are studying. These chapters are very easy to read, and you can read these chapters in 2 to 3 days. All the chapters you can read in 2 to 3 days. You just need to have focus, and you will be able to understand whatever we have been teaching. The last three chapters, chapter 11, 12, and 13, will be discussed day after tomorrow, same time at 10 a.m. The first 10 chapters you should read and come after day after tomorrow. Is there any question you want to ask? Any doubts? Disha, Priya, any questions?
No, sir.
No, sir.
Everything is clear?
Yes,
Yes,
sir.
sir.
Okay, then please read and come. Day after tomorrow, we'll discuss the last three chapters, chapter number 11, 12, 13. Then this course will be over, and then my colleague will start with the next course.
Okay, sir.
Okay, thank you so much for
Thank you.
listening patiently. Okay, thank
Thank you,
you.
sir.
Thank you, sir.
Okay.